Inside your body, right this second, there's a constant, high-stakes drama going on. It's the story of an incredibly powerful army that has to learn the difference between friend and foe. We're talking about immunologic tolerance. And, well, if it gets it right, you're safe. But if it gets it wrong, that army starts a devastating civil war against its own side. So your immune system is this amazing, sophisticated army, you know? It's constantly hunting down and wiping out invaders, like the bacteria you're looking at right now. It's unbelievably powerful. But that very power brings up a huge question. With all that firepower, what stops this army from turning on the very thing it's supposed to protect, which is you? Okay, here's our game plan for today. We're going to start with the fundamental problem the immune system is trying to solve. Then we'll nail down exactly what tolerance means. After that, we'll peek inside the basic training facilities where this all gets learned, and then check out the backup systems out in the field. And finally, we'll look at what happens when the whole system goes haywire and leads to autoimmunity. So first up, the immune system's dilemma. I mean, just think about it for a second. This system has to be aggressive enough to kill off deadly germs, but at the same time, gentle enough to leave your own trillions of cells completely alone. It's a total tightrope walk, a constant, delicate balance between attacking and controlling itself. And what I love about this image is how it shows you that balance. See, on one side, you have your effector T cells. These are the frontline soldiers, the ones who actually launch the attack. But on the other side, you've got regulatory T cells, or TREGs. You can think of them as the military police. Their whole job is to keep the soldiers in check and make sure things don't get out of hand. The goal? Perfect equilibrium. So, why is this regulation so incredibly important? Well, for one, you don't want your immune system causing a ton of collateral damage when it's just fighting off a common cold. But the biggest reason, and this is really the heart of our discussion, is to stop it from attacking your own body. We call this self-tolerance. When that control breaks down, that's when you get things like autoimmune diseases. So how does this system actually maintain this delicate balance? Well, it follows a very strict set of rules of engagement. And that brings us right into our next section, where we're going to define our main concept for today, immunological tolerance. So let's break it down. At its core, immunologic tolerance is just the immune system's learned ability to ignore its own stuff. It sees a self-antigen, a little protein piece from one of your own cells, and it knows, okay, stand down. It's a state of unresponsiveness, but it's specifically towards you. And to really get this, we need to know two key terms. An immunogen is anything that triggers an attack. Think of a virus, that's a classic immunogen. A tolerogen, on the other hand, does the opposite. It tells the immune system, hey, stand down, this is friendly. In a healthy body, all of your own cells are basically showing tolerogens. So where does this all-important learning actually happen? You can think of it as happening in two main zones. First, there's central tolerance. This is like a heavily guarded boot camp, located in the thymus for T cells and the bone marrow for B cells. Then you've got peripheral tolerance. This is the ongoing security protocol that's active everywhere else in your body, out in the peripheral tissues. Okay, so let's start at the very beginning, at the academy. Section 3, Central Tolerance. This is the boot camp where every single new recruit for your immune army gets put through its paces. So, deep inside the thymus and bone marrow, these brand new, totally green immune cells are faced with a critical test. They're shown little pieces of you, self-antigens, and how they react in that one moment, well, that decides their entire fate. The first possible outcome is, frankly, pretty brutal. If a new lymphocyte grabs on way too tightly to a self-antigen, the system flags it as a potential traitor, and it gets eliminated through programmed cell death, or apoptosis. This is called negative selection, and this is a really, really important concept. It's the system's first and most ruthless quality control check to get rid of dangerous cells before they're ever deployed. Now, fate number 2 is super cool, and it's unique to B cells. If a B cell's receptor happens to recognize a self-antigen, it gets this incredible second chance. It can literally go back and edit its own genes to build a brand new receptor that is no longer self-reactive. It's like an on-the-fly software update to make sure it doesn't cause any trouble. And this brings us to a third and totally brilliant option. Some T cells that recognize self-antigens aren't deleted at all. Instead, the system repurposes them. It converts them into those regulatory T cells, the TREGs.
So they graduate from boot camp, but not as soldiers. They become the military police, and they're sent out into the body with one single mission: keep the other soldiers in line.
But, no system is perfect. What happens if a potentially dangerous cell manages to slip past all that central training? Well, that's where our second layer of defense kicks in: peripheral tolerance. These are the safeguards designed to keep any rogue cells in check. So just imagine for a second, a self-reactive lymphocyte has graduated, it's out there circulating in your blood. It's basically a ticking time bomb. The moment it encounters a self-antigen out in the field, a whole new set of safety protocols get triggered to disarm it. The first way to disarm it is something called anergy. See, for an immune cell to really go on the attack, it needs two signals. The first is seeing the antigen. The second is a confirmation signal, like a battle alarm that says, danger, this is a real threat. Your own self-antigens don't provide that second danger signal. So the cell sees self, gets no alarm, and is basically put to sleep. It's still alive, but it can't fight. The second outcome is one we've seen before: apoptosis. That's right, just like in boot camp, self-reactive cells can be deleted out in the periphery too. If they keep getting stimulated by self-antigens over and over without the right context, it can trigger their self-destruct sequence. And the third outcome is suppression. This is where those T-regs we talked about, the military police, really earn their keep. They patrol the periphery and they actively seek out and shut down any self-reactive lymphocytes they find. This isn't just a passive system, it is a vital active surveillance operation to maintain the peace. This whole two-signal idea is so important. Let's just look at the molecules for a second. Think of it like a car. The first signal, the antigen, is like putting the key in the ignition. But to actually start the engine, you need that second signal. The go button is a molecular handshake between CD28 and B7. But just as important, there's an emergency brake. A different molecule, CTLA4, can slam on that brake, shutting the cell down. Which brings us to our final and really critical chapter: autoimmunity. This is what happens when all of these elegant, beautiful mechanisms of tolerance fail, and that immune system civil war actually begins. So what causes everything to break down? Well, we generally think of it as a kind of two-hit process. First, you've got genetic susceptibility. Someone has genes that make their immune system maybe a little more likely to make mistakes. But that's usually not enough on its own. The second hit is an environmental trigger, a lot of times an infection, that comes along and just pushes that susceptible system over the edge, causing it to lose self-tolerance. All right, let's wrap this all up. These are the absolute must-know takeaways. First, central tolerance. That's the boot camp, where self-reactive cells are either deleted or repurposed into Tregs. Second, peripheral tolerance. That's the vital backup system, using energy and suppression to disarm any threats that escape. Third, don't forget that special trick just for B cells: receptor editing, their unique second chance. And finally, the big consequence. When all of these layers of defense fail, the result is autoimmunity. So we've seen how tolerance is the guardian of our internal peace. And this really leads to a huge question for the future of medicine. If we could learn how to become the master controller of this system, to dial tolerance up when we need to stop autoimmunity, or maybe dial it down to better fight cancer, could we be on the verge of curing some of the most difficult diseases we face?